Okay, thank you everyone. Thanks for the introduction. I'm Pepe Vila, and this is a joint work with Boris Kov and Jose Morales. So let me start talking about what are eviction sets. We all know that all our computers have these small memories for speeding up computations that are called caches. And we usually split these caches into slices, and each slice has several cache sets. And each of these cache sets has capacity for associativity many memory blocks. So what we are interested in is on finding addresses that collide in cache. And this means addresses that are mapped exactly into the same cache set. And specifically what we want to do is find the associativity many of these colliding addresses, and this is what we will call an eviction set. The idea is if we access this eviction set, we will completely fill the content of this cache set, and therefore evict all the previous content. So why is this interesting? Well, it turns out that for many microarchitectural stacks, finding a small eviction set is a key primitive. For instance, for prime and probe, the attacker needs to put several cache sets in a control state. And this is done by filling the cache set with its own control data. For row hammer, the attacker wants to activate a DRAM row with enough frequency in order to cause bit flips. And in order to do that, it needs to bypass the cache. So one way for doing that, again, is using eviction sets to remove the data from the cache. And finally, some variations of spectra we have seen in the first talk require to evict a specific content from the cache in order to increase the speculation window and be able to leak content. So the question now is, why is this a challenging problem? Well, it turns out that in some cases, the attacker may not know the mapping from physical addresses into cache sets. Or even if this mapping is known, since the attacker usually runs from user space, he doesn't know the translation from virtual addresses into physical addresses, and therefore it doesn't know the mapping from virtual addresses into cache sets. And there are some scenarios where this is even worse. For instance, when the attacker runs from JavaScript, there is no even notion of virtual addresses there. So the only thing that the attacker has are array indices, and we need a way to find how this can map into specific cache set. So again, we are interested in finding associativity many elements, whatever these elements are, virtual addresses or JavaScript array indices, that collide in the cache. The contributions of these papers are three. The first is that despite that eviction sets have been extensively used in the past, there was no systematic study of the problem. So we provide this first systematic study on the problem of finding eviction sets. We also show novel algorithms that allows us to find these eviction sets in linear time compared to the previous quadratic approaches. And finally, we perform a reliability and performance evaluation of these algorithms in real hardware. And this is important because, as we will see now, this contribution is not only a theoretical improvement, but really our algorithm is easy to implement and provides a crucial performance increase in practice. So let's see how can we find these eviction sets. The general approach is usually twofold. First, we want to find a large eviction set for a certain address V. And once we have this large eviction set, we will try to reduce it into its minimal core. So in order to find a large eviction set, we usually only need to pick enough addresses at random. And for the precise definition of enough, I'll refer you to the paper. But the idea is that since we don't know into which cache set an address is mapped, by picking just randomly a bunch of addresses, the more addresses that we pick, the higher the probability that this set of addresses will contain at least associativity many that go into the specific cache set. So once we have a set of addresses, what we can do is use a timing test to check if this is an eviction set. And the timing test works as follows. We will first access a victim address. Now this address will be in the cache. And then what we do is we access all the elements in our candidate set. And finally, we measure the access time to the first victim address again. If the access time is fast, it means that our victim is still in the cache, so our candidate set does not contain at least associativity colliding blocks, and therefore it's not an eviction set. On the contrary, if the access time is large, it means that our victim is not in the cache anymore, so our candidate set set contains at least associativity many addresses and therefore is an eviction set. Just a small remark, in order for the caches to behave like this, we need to do some assumptions on the replacement policy. But as we'll see later, this assumption is not a limiting factor in practice. So for this talk, I will focus on the second part of the problem. Once we find this large eviction set, how can we reduce it into its minimal core? And for that, let me quickly explain the commonly approached algorithm until now. We start with a set of addresses of size n. This is an eviction set. And what we will do is we pick an address and test the remaining set. If the remaining set is still an eviction set, we can just discard this picked address because it's not part of its minimal core. And we repeat this process several times until eventually we will remove one element that makes our set to stop being an eviction set. So at this point, what we learn is that the picked address is part of the minimal eviction set. So we need to keep track of it, insert it again on the set, and repeat this process until we identify associativity many of the addresses that represent the eviction set minimal core. So this algorithm is nice, but the problem is that the complexity cost in number of memory accesses is quadratic on the initial size of the set. And the natural question that we ask is, okay, can we do better than this? But before answering to that, let me quickly talk about group testing and threshold group testing. The problem of group testing was first studied by Robert Dorfman in 1943 in the context of identifying all the syphilitic soldiers in an army. And his key insight was that imagine that we have a population of blood samples, and if the ratio of defective elements, or if infected samples in this case is small, we can find all the defective elements more efficiently than by just doing individual tests. So what we can do is, if we split this into groups of size 5, by using a test on this group, if the test is negative, we automatically can discard 5 elements with a single test. If the test is positive, we'll need to split it in further groups. So the problem of group testing studies what is the optimal size of these groups, or what needs to be the optimal size of these groups in order to identify all the defective elements in the minimal number of tests. And as you can imagine, this had a lot of applications in practice, and a lot of people studied variations and generalizations of these problems. And we are specifically interested in a generalization by Peter Damaschle from 2006, where the goal is the same. We are interested in identifying all the defective elements of a population, but in this case, the test is slightly different. Our test will only give a positive answer if the group contains at least U defective elements. And it will give a negative answer only if it contains at most L defective elements. And it can be either positive or negative answer with a random probability in any other case. So our key observation here is that our test for an eviction set is actually a threshold group test. If you think about how this works, our test will only give a positive answer if the set contains at least associativity many addresses. So with this insight about threshold group testing, we designed the following algorithm. And the settings here are the same. We will start with a large eviction set of size n. And this time what we will do is split this set in associativity plus 1 subsets. So if we imagine that in the worst case, this eviction set contains only 4 defective elements, what we are interested is in to find a union of these subsets that is an eviction set. And the interesting part is that in the worst case, at every iteration, we can always remove at least one of these subsets. So at each iteration, we are discarding a factor of n number of elements. And if we keep repeating this process, we will end up with our minimal eviction set. And in our paper, we show that the cost in number of memory accesses, the worst case cost in number of memory accesses is linear on the size of the initial size, of the initial set, sorry. So, okay, this is a good theoretical result, But in order to see how this works in practice, how well this works in practice, we implement the algorithm in a tool that is public. And this tool can be run, well, we can run it on different machines with different cassette settings. And we can use it to model adversaries with, or attackers with different capabilities. For instance, here we have three figures. The first one represents an attacker that has complete information about the set index bits. So it only needs to pick a few addresses to find a large eviction set and then reduce it. The second figure represents an attacker with partial information about the set index bits. And this last one is an attacker without any bit of information about the set index bits. So this is average real execution time of the reduction. And we can see that in the first case, since the initial sets don't need to be too large, reducing a set of 200 or 300 addresses, the performance benefit is quite modest. But with partial information, we already see that the sets that we need to reduce are 2,000 or 3,000 addresses. And in this case, we start seeing a performance improvement of almost 3 orders of magnitude. But the most interesting case is the last one, where the attacker has no information at all about the set index bits. In this case, you can see that the sizes of the sets that we need to reduce are 30 or 40,000 at least. And in this case, the baseline algorithm becomes completely impractical, because for finding a single eviction set, we need to spend several minutes. While using group testing, we can do it in less than 2 seconds. And this is a very good result, because there were some proposed countermeasures that were trying to hide this mapping from addresses into cassettes. So with our group testing, we can see that even if this mapping is completely unknown to the attacker, it's still possible to find minimal eviction sets. Okay, so this is about performance, but before I say that we did some assumptions on the replacement policy for our test to work. And it turns out that in modern replacement, some modern replacement policies break our assumptions on the test, and this introduces errors in our algorithm. And this is a nice example extracted from a Skylake machine, where we can see on the horizontal axis the different cassettes on this machine. And the green bars are the reduction rate without error. So how many times we were able to reduce a large set without having any error. And we can see that there are a few cassettes that really behave as we assume, and the error rate there is very low. But in the majority of these cassettes, the replacement policy is slightly different, and this introduces a lot of errors. The good thing is that in practice, we can use some heuristics like based on repetition and backtracking, and with that, we are able to successfully reduce the eviction set for any cassette with only a small performance overhead. And in order to convince you that this really works well in practice, I implemented our algorithm on a web browser. Can you, sorry. Here we will be running a web page which implements our reduction algorithm in JavaScript. And here we will see that, let me start. What we are doing is that our JavaScript found some array indices that correspond to an eviction set. And here what we are doing is we are attached to this browser process, and we translate these indices into virtual addresses and then into physical addresses to check that effectively the indices correspond to colliding addresses. All these JavaScript array indices will be mapped into the same cache set. And we can see that if we try to find all eviction sets, the performance is really good, and the reliability, as you can see here, is also very good in practice. So here, in these few seconds, we found 73 different eviction sets, and for each of these 73, we can automatically compute 64 more. So we found 73 times 64 different minimal eviction sets. So just some, as conclusions, some final remarks, and the most important one, I think, is that finding minimal eviction sets is a threshold group testing problem. And this provides an important insight for when we try to think about principal countermeasures. And also there is another, there are some variations of threshold group testing that can be useful to improve even these algorithms even more. For instance, we did some assumptions that introduce errors, and we have this performance overhead to our heuristics, but some variations of threshold group testing work with noisy tests. So we think that using this notion of noisy group testing, we can reduce the overhead of these heuristics. And finally, well, we show a novel linear algorithm time that makes attacks much faster in practice, and in some scenarios, as when the attacker has no information about the set index bits, the attacker becomes really practical. And that's it. Thank you for your attention, and I'm happy to take questions.
Hi, my name is Guru Raj from Georgia Tech.
Yep.
Excellent talk, loved it. So I'm from the computer architecture community, and in that community, there's been some interest in trying to make this task of discovering eviction sets harder. So my question was, if people try to sort of try and randomize the cache indexing function, or come up with ways to introduce non-determinism in the indexing itself, so that would make the task of discovering eviction sets harder, but my question is, how would you sort of try and adapt your discovering algorithm to adapt to the changes in the indexing function itself?
Well, if these changes are, these changes, even if you completely randomize the mapping from an address to a cache set, this mapping needs to be static in order to get some benefit from the caching mechanisms. And if you do that, what the attacker can, the only information that the attacker has is that there is no, he has zero bits of information from this mapping. So this is actually the last of our case. It's harder to find this large eviction set because you are picking addresses completely at random, and you will need 30 or 40,000 of these addresses. But even in that case, we are able to reduce it in less than, I think, 2 seconds. So yeah, even if you completely randomize this mapping, it's possible. I guess this is the key insight. It's still possible to find the minimal eviction sets.
I guess I'll follow up on that question. So, okay, I get it that if I do a one-time remapping, let's say truly random remapping. Now, if I add more dynamism, whatever, I can't say it. But if I make it more dynamic, and at runtime, and I do it every 5 seconds, 10 seconds, pay some performance penalty, how would that affect your approach?
I think that the problem is that if you do it at runtime, then when you want to access just as a legitimate program, not as an attacker, you want to access your data, you will not find it in cache because you are being mapped somewhere else. So this would introduce a performance into a real problem. So I don't think that this can be really a mechanism that you can implement in practice. What you could do probably is maybe in some scenarios you can find a trade-off between how much you affect good programs and how much harder do you make to find eviction sets. The problem would be if there is completely a dynamic mechanism that change the mapping to eviction sets, the attacker will need to just recompute them several times. If you can do it fast enough, it's probably fine. But yeah, I guess that this is like an open question. Where is the trade-off between making things harder and affecting the performance of good programs?
Right, and so if you had an environment like SGX, where you're saying, I care about the security of this, and it already has an expensive context, which maybe you could tolerate that price to kind of make sure that that's security critical code. A lot of interesting work, a lot of interesting follow-on work. Let's thank our speaker one more time. Thank you, Pepe.